This is the masterclass video for the topic of general wave properties. Transverse versus longitudinal waves. What is the difference? A transverse wave is a wave in which the direction of wave motion is perpendicular to the vibrations of particles. You can see from the figure that for a transverse wave, the particles vibrate vertically up and down, perpendicularly at 90 degrees to the wave motion represented in black. For a longitudinal wave, the direction of the wave motion is parallel to the vibrations of the particles. So the particles vibrate left and right horizontally. What are some examples of transverse and longitudinal waves? Sound wave is the only example of longitudinal wave that you learn. Transverse waves, all the 7 electromagnetic waves, gamma rays, X-rays, ultraviolet radiation, visible light, infrared rays, microwaves, radio waves, as well as water waves, all the 8 waves are examples of transverse waves. And these are the two equations which we use commonly in this topic. V equals to F lambda. The speed of the wave is the frequency times the wavelength. The period of the wave is the reciprocal 1 over the frequency, or the frequency is 1 over the period, the reciprocal of the period. Examples. Question 1. What is meant by the term wavefront? A wavefront is an imaginary line joining identical points of a wave. C. There are two kinds of wavefronts. Straight lines, which we call plane wavefronts, or circular lines, which we call circular wavefronts. Whether is it plane or circular wavefronts, the distance between two wavefronts is called the wavelength. 2. We look at the first diagram. Draw a horizontal line across the figure. The highest points of the wave are called the crests or the peaks, and the distance between two consecutive crests or peaks is called the wavelength. The maximum displacement or the height of the wave in this case, Q, is called the amplitude of the wave. We now look at the second figure. The vertical lines given, for example R, are called plane wavefronts as we saw earlier. A quick recap again, that a wavefront is an imaginary line that joins all identical points of a wave. And we also learned that the distance between two wavefronts is called the wavelength. Therefore, the letters that represent a wavelength are either P or S, and a wavefront is represented by the vertical line R. So the answer is A. Question 3. We are given two types of graph. First, displacement distance graph on the left and a displacement time graph on the right. We can see that the y-axis for both graphs is the same, representing displacement. The difference is in the horizontal x-axis. The y-axis displacement will give us the same physical quantity. The maximum displacement or the height of the wave is represented by the amplitude. For the x-axis, from the first graph, the x-axis is representing distance. So the distance of one wave is called the wavelength, lambda. For the second graph, the x-axis is representing time. The time taken for one wave is called the period, t. We can see from the second graph that the period t of the wave is 0.04 seconds. We apply the formula, frequency is 1 over period. We substitute the period of 0.04 seconds into the equation. Frequency is 25 Hertz. Hertz is the SI unit for frequency. Next, we can see from the first graph that the wavelength lambda is 2 centimeter. We're going to apply the formula V equals to F lambda. Speed is frequency times wavelength. The frequency has been found earlier to be 25 Hertz, multiplied by the wavelength of 2 centimeters from the first graph. The speed of this wave is 50 centimeter per second. D. Question 4. These circles that we see are called circular wavefronts. And earlier on, we learned that the distance between two wavefronts is called the wavelength, lambda. So in this case, the wavelength of this wave is 6 centimeter. From the question, we can also learn that the wavelength is 6 centimeter. The distance between crests is 6 centimeter, and the distance between crests is known as the wavelength. The first sentence of the question tells us that in 2 seconds, 3 wave crests are produced. In 2 seconds, 3 waves are produced. So in 1 second, 1.5 waves are produced. This tells us that the frequency of this wave is 1.5 hertz, because frequency is the number of waves produced in 1 second. With the frequency as 1.5 hertz and the wavelength as 6 centimeter, we're going to apply the formula to find the speed of the wave. V equals to F times lambda. Speed is frequency times wavelength. Frequency of 1.5 hertz multiplied by the wavelength of 6 centimeter will give us the speed of this wave as 9 centimeter per second. D.